from Google, and it's about scalable RL for system where offline imitation from multiple baselines, a case study in compiler optimization.
Hi, everybody. First, I would like to thank the organizers for putting the workshop together. And this is joint work with my collaborators, Alek Agarwal and Mircea Trofen, both from Google. Okay. So we are faced with the following standard kind of systems problem, where we have a system. There is a request that comes in. We need to make a sequence of decisions and receive an output. Then the output is evaluated against some set of metrics that we care about. How can we solve this problem? Well, one, experts in the field can design handcrafted heuristics. Two, we can apply supervised machine learning. Or three, we can apply RL algorithms with which you are mostly familiar from all the talks given today. Now, I would argue that RL is probably best suited for this type of problem, as it is a principled framework for sequential decision-making settings. I'm not going to sell RL too much to this audience because you kind of all know the advantages already, but I do want to talk a little bit more about the disadvantages. In particular, it is very often the case that the system that we're dealing with allows no randomization, while RL algorithms do need randomization to explore and often produce randomized policies. Further, if we have a complicated system, it might be hard to simulate it, or it might be hard to get a reliable reward signal, and proxy rewards often are not good enough. Finally, if we have a complex system together with a complex learning approach, the results might be of questionable quality. A lot of academic work has been done to address these problems, but it is still very important to verify how well these RL approaches scale and how well do they work in practice. And probably, as many of you have experienced firsthand, they might not necessarily always work very well in practice. I'm going to talk about another method similar to RL that is going to try to address these shortcomings in the context for inlining for size problem, with the disclaimer that our method is very general and can be applied to broader systems problems. So very quickly, what is inlining? Inlining is the process of replacing function call by the body of the function and can significantly simplify the code, the resulting code, which in turn can lead in reducing the size of the compiled binary. Here we are interested in reducing the size of the compiled binary as a use case. Okay, how would a typical RL-trained inlining policy work? Well, we have a program that consists of multiple functions. The inlining policy gets to the first function and decides it wants to inline the function. Okay. It inlines the function, it moves on to the second function, it again has a decision to make to inline or not to inline. Here it might decide not to inline, and then the process continues until all of the functions are exhausted and the program is compiled and we have a binary. We measure the binary size as a reward function or as reward signal for our RL algorithm. And then we do an update step of the RL algorithm, which is usually maybe like some gradient descent step. This type of learning has already been applied for compiler optimization, specifically inlining for size by the LLVM community. Our approach, instead, is based on imitation learning and works in the following way. We assume that we have a set of baseline policies. These baseline policies can be anything. They can be handcrafted heuristic policies designed by the compiler experts. They can be machine learning trained policies trained by maybe evolutionary strategy or RL-based policies. With the set of these baseline policies, we take a big corpus of programs and compile each program in the corpus with each baseline. We measure the resulting sizes and pick the best policy for program based on the size. After that, we are going to try to imitate the actions of the best program per size or the best policy per program. Okay, here is an example of how this is going to work. We have two programs and two baseline policies. For the first program, policy pi1 gives the smaller size, so this is the policy that we're going to try to imitate. For the second program, we have policy pi2 giving us the smallest size, so this is the one that we're going to try to imitate. Meaning, at the end of the day, we want to learn a policy pi new, which acts exactly as pi1 on program 1 and as pi2 on program 2. Okay. Why am I arguing that this is more beneficial or a better approach than standard RL? Well, first, here we have a richer learning signal. In particular, we get to get a signal per function in the form of the action that our best baseline policy took, as opposed to RL, where RL is only going to get a signal for the compiled binary in the form of the size of the binary. This actually helps lowering the variance of learning, resulting in policies which incrementally improve over our baseline policy, as opposed to typical RL algorithms, which might exhibit some fluctuation during the learning process, where the policy might degrade in quality sometimes. Further, our algorithm is based on simple supervised learning setup, so it has very few hyperparameters to tune as compared to typical RL algorithms. Also, here, compilation and learning are interleaved in the following sense. We take the whole program corpus and compile it. We take the results of that compilation and then run the learning algorithm to convergence, as opposed to RL algorithms, which usually would compile a few programs at a time, then get the reward signal, maybe make a few gradient steps to improve, and then would have to compile again. Finally, we can bootstrap our method by adding every new policy that we train to our set of baseline policies, resulting in even a better performance. Okay, so where have we deployed our results? We have pretty good results for Chrome on Android on high-end devices. This is actually currently deployed, so if you have an Android phone, it is running on your phone. We start with a single baseline policy trained by PPO, and we do this bootstrapping. We save what is considered as a significant size savings by the Chrome on Android folks. We also deployed our algorithm to train a policy for the Google Search app. We have similar improvements there. And there we started from a set of two baselines. One trained from an evolutionary strategy algorithm, and one was a heuristic policy crafted by the compiler community. I want to emphasize that, again, this work extends beyond the inlining or compiler problem, and we're very excited to actually try it for other systems-related work. Please, if you have some kind of nice problems, come talk to us. We'd be very happy to chat. That's it.
I think we're going to take questions now, but the next speaker can come and try connect your computer. So question from the audience?
Hello, hi. Thank you for the talk. I'm Frank. I wanted to ask if you could maybe explain or comment on how do you go about representing the search space in an RL setup of this inlining problem you described?
Yes, of course. So the state space is usually some handcrafted features by compiler experts. These features can be something like the number of calls to the function that you want to inline, or the number of functions that the function that you want to inline calls. I'm not a compiler expert, so I cannot give you other examples, but this is how the state space looks like. action space is obviously like to inline or not to inline.
More question? I think I see a hand over there. Oh, maybe it's a different.
Very interesting talk. So you talk about like compiler optimization. I wonder whether this methodology can also be generalized or expanded to other systems like scheduling problem, like resource allocation problem.
So that's a very good question. We expect that we can extend our algorithm to such systems. The only thing we really need is a reliable enough reward signal to be able to distinguish which policy is kind of the best for the current instance, and a set of baseline policies. But the set of baseline policies kind of comes by default because there's clearly already a deployed policy for any problem of interest that you probably have. So, yeah.
All right, one more question.
Thank you for the nice talk. Is there a way to replicate the results? In other words, is the model open weight or any other way?
So I would tell you to look at the paper because we link to the policies that the experiments are run on. And also from what I know, the Chrome on Android is like kind of open sourced. So you can collect a data set and run your own algorithm to compare. So pretty much everything should be reproducible in this paper. There's like nothing. Also, we are checking in our code for our algorithm in the MLGo GitHub repository. So you could even run that.
All right, thank you for the great talk. And the next one is our last talk of the day before the poster session. We have Siva Hari from Nvidia, and he will be presenting WarpDrive, an agentic workflow for Ninja GPU transformations. And hopefully the slide works.
Let's see. Okay, there it is. Okay, well, welcome to this talk. I'm going to be talking about this ongoing project. I want to be very clear, this is work in progress, which we are calling WarpDrive. It is to help Ninja, to apply Ninja GPU transformations through agentic flow. The primary author for this work is Sana Damani. She couldn't be here because of visa issues, so I'll be presenting this work. Well, the motivation, I won't spend much time here. GPUs have become powerful accelerators for a wide range of applications, going from AI, graphics, robotics simulations, and physics simulations, and so on. And people want to write efficient GPU code so that they use the GPU's resources well, they can get the results faster with using less energy. However, there are some challenges in writing high-performance GPU codes. Usually the very first step is you want to understand the performance characteristics of your current workload, how well it's using the resources, where it may be overusing some resources or underusing some resources, so that you balance it to get the best performance. And users, developers usually have significant what we call ninja skills. They may have to tune for occupancy to get better use of the resources. They may have to use concurrency using streams, fusion to get better performance, speculative reconvergence to perhaps reduce divergence in their programs, better shared memory padding to perhaps address bank conflicts. And this is a small list to what we think it is. And this can be manual process, so people have to spend some time to improve their code. So what we're trying to do, so let's look at first what the debugging flow today looks like. So somebody wants to start as an input program, and their goal is to get high-performance optimized code. That's the goal, right? And the first step is you will use the profiler that NVIDIA has built, or there are other profiler tools like Nsight Compute or Nsight Systems to get insights into your workload. After this, let's walk through an example. Let's say you found that there are some idle resources, and you think concurrent execution of few kernels may help relieve that. At that point, the next step any human would apply is to come up with an optimization plan which would include, let's detect where what the independent kernels are, and co-locating them can help optimize the workload. And we will apply the transformation to the code, and that's where we get to our optimization code. But that's not the end. We will do some correctness testing, and if that may be, in this case, you verify that the transform code has the same dependencies as you want it to be after it is done, and this debugging loop goes on. And then afterwards, you do the performance testing, and if you think your bottlenecks are relieved, you're good. Otherwise, you go back and then probably try a different optimization or reapply this transformation, right? And in this process, as I was saying, baseline currently today is somewhat manual. You need a lot of expertise, ninja programming skills to even understand the optimizations and apply them. What we are proposing is WarpDrive, an agentic workflow to help optimize this flow and make it easier for the developers to use this. This is very much work in progress. The LLM agents in this case, we tried a few, and then we are using React-based agents. You must be familiar with this, so I won't go into it. Essentially, thought, action, and observation loop. We provide a bunch of tools to each of the agents to help perform those tasks better. Especially for the profile analysis, let's say the tool essentially is an Nsight compute or Nsight NCU tool, and once you have the report, you can use a Python interface to extract information to understand where the bottlenecks are, and use that to identify some optimization suggestions. I'll be happy to go over the details of the tools later on at the poster. And we set up the agents through the prompting mechanisms. A chain of thought really works well for us, based on the examples we have looked at. And few-shot prompting also helps. So let me walk you through an example just to illustrate what we're trying to do. Let's say, as I was talking about this application, let's say we have 3 kernels, and these are launched in sequence today. You have kernel 1, kernel 2, and kernel 3. And you can see that the kernel 3 is dependent on the first 2 kernels, but first 2 kernels, let's assume, can run in parallel. And the first step after the profile analysis, let's say we determine that concurrent execution will help. Then the optimization step is, in this case, will be customized so that the agent will detect independent kernels, either through code inspection or running some tools. That's the job, is to come up with that dependence graph. After the dependence graph, there's next step is to assign streams so that those kernels can be run in parallel. And then you come up with that optimization plan, which is you have kernels over here. So you assign stream 0 and 1 to 2 kernels that can run in parallel, and you synchronize before the third kernel executes. And this helps the code generator because now it has steps to follow based on the optimization you're interested in. And then the generated code may look something like this for this example, where streams are assigned to the first 2 kernels, different streams, and you have a synchronize before you proceed. And the correctness testing in this case was to use the existing test set. Since we start with a baseline working workload, we assume that there exists a testing harness or that we will use. We also do additional testing in this case. That is, after the generated code, we use another agent, and we can also use another tool to derive the dependence graph from the generated code and compare that to what we intended to use as an additional step for correctness testing. I'll go into detail, but there are a lot of open problems in this, and there are previous talks were also talking about this. And then we will check for speed up if that's good, and that's what we did in the prototype. So here are very preliminary results. These are on small workloads. We would call it micro benchmarks at this time. And when we go through the flow after some iterations and find adjusting the flow, we get up to like 1.3x speedup in this case. But optimizations can be applied at different level. There were earlier talks about looking into maybe compiler options or hints. These will have less correctness issues. So on the x-axis, we show logically correctness issues, right? The more code you change, the more correctness issues you will have. Compiler options and hints fall on the side where there is less correctness issues. And for some of the options, you will not have any correctness issues. And the y-axis is opportunity. The more changes you make, you can get more performance opportunities. And so we would like to be in that, but perhaps have this flow to help achieve better opportunity. And so we tried, these are again preliminary results. We tried on some micro benchmarks, some optimizations at each of these levels. For the compiler option, we tried just setting the register target, that helps. Compiler hints, we tried some, and we were able to get some speedups on the small benchmarks. For kernel level, we tried shared memory padding only for the workloads that suffer from bank conflicts. And at the application level, the stream assignment that I was talking about and kernel fusion. So I'll stop here. There are many unsolved problems, many challenges, and future work for things that we have to do. This is early work, so we are here to get feedback and to show you what we're trying to do. We want to expand to more realistic workloads. Input context length is one of the concerns, or rather limitations that we have, that if the code base is too large, we can't really provide it. We need better navigation tools to identify the relevant sections. Program verification is an open research problem at this time. I'll be happy to talk more. We have some ideas, but we are happy to gather more input on how to address that problem. We use some prompt helpers in this case, but we want to figure out how we can set our agents in a more automatic fashion. That'll be pretty useful. And probably have more complex formulation of the agents so that they can address even harder problems. Thank you.
Question from the audience?
Hi, thanks for the talk. Are you going to create data set to train those agents? And another thing is, I guess a lot of tools are closed source. So so I guess, do you have the sort, you using those agents to invoke those tools, you use those as an end-to-end pipeline, or you actually modify the modify the source code of those Nvidia tools to apply this agentic?
Okay, so about the first question, the data set, I think it is an important problem. We can use some data sets. We are looking into it, but if you have some ideas, please let me know afterwards. On the second problem, tools, some of the tools were custom made based on the task, especially when so there are many tools that we used. If you're referring to the Nsight Compute or Nsight System tools, there is a Pythonic interface to it through which you can write a program to extract information from that tool. And so we just provide in context some examples how to write that Python code. And so tool essentially just runs that Python code and then it extracts the information from the tool, from the report, the profile report. And some of the other tools are essentially the dependence graph. You can, depends on in Warp, they provide a tape facility where you can know when the kernels are launched. And so we use that information on the objects, when they are launched, to make the dependence information. So these are, some are custom tools, some are using interfaces.
Next question.
Hey, thanks for the talk and really cool work. You kind of answered this question, but I want to dig into how you're getting the information from Nsight Compute into the model. Because I'm sure you used Nsight Compute. It has tons of, like, deluge of data.
Yes.
And so do you prioritize some of that data? Are you just dumping it by text into the model? And how do you, like, trade off analysis data from Insight Compute versus context in code?
Yeah, I'll be happy to chat with you in more details on this later, but the short answer is there are a lot of metrics in there. We have a high-level Python interface to extract information from the report. So to clarify, when we run the workload through Insight Compute, we get a report file from it, which has all the profile information in it. And we just need to look into it, and based on the optimization, we set up to what to look for it. And we can, that agent can enhance over time to automatically detect what to use. Insight Compute also provides a lot of recommendations inherently, and that information can be used. There are some more advances we make into that code where the metric table comes out is often hard to digest by the model, so we just have another Python program which is generated to get relevant information through it.
Okay, very cool. And just a quick second question. Have you tried generalizing on other architectures? Like, have you done like Volta, Ampere, Hopper, or just single architecture?
It's a good question. So far only single architecture, but yeah, we would like to at some point look into other architectures.
Okay, very cool. Thank you.
Okay, one more question.
I'm curious, so currently here there's no human in the loop.
Correct. Okay, proceed with your question.
I'm curious whether you've like experimented with like
Yes.
human plus agents, and also
Yeah.
when you said improvement over baseline, are those codes already like incredibly optimized, or they're
No.
like very baseline codes?
No. Our examples are very basic, so they are not optimized code. We are just trying to see how much potential there is. Your comment about is human involved? We absolutely think human will be involved in many of these places. This is an early prototype to understand the capabilities of this agentic flow, because we know there are people who are very concerned if an agent changes the code. They want to be in charge, and we totally respect that. What we're trying to achieve perhaps here is to do some ablation studies earlier to give information to the developer about what potential exists when this optimization is applied, and provide all the information about the profile information and potential how to apply that optimization, and hopefully that information will be useful. While we're trying to do end-to-end, but we hope each individual component will be helpful in its own merit.
Okay, let's thank you, the speaker, again.
Thank you.
Okay, and I think this is the last talk of our workshop, but then we still have poster outside the room, so please hang out and talk to all the others of the papers. And thank you everyone for staying until the end. Thank you for all of our co-organizer, our speakers, and also our stream engineer over there who sit there and make sure that our stream is working properly.